Hello guys, this is Prime Concepts. In this video, we want to consider another optical instrument. We have already established or explained the concepts behind the eyes as an optical instrument, the simple microscope as an optical instrument, the compound microscope as an optical instrument. So in this video, we want to consider another optical instrument, which is the astronomical telescope. The telescope, astronomical telescope. So that is what we want to consider. Now we have different types of telescope, but this would be the focus of our study. One type of telescope we have is astronomical. We have the Galilean telescope. We have the terrestrial telescope. We have these types of telescope because the Galilean telescope was made by Galileo Galilei, right? So he was the first person that made the telescope for studies. And then other ones, Newton also made his telescope and others. So, but we want to consider the astronomical telescope in this video. A telescope in general, a telescope is an optical instrument or device that is used to view distant objects that are very far. So the telescope is an instrument for viewing distant objects. While we mentioned when we were studying compound microscope, that the compound microscope is an instrument for viewing close, near objects and getting a high level of magnification for them. The telescope, on the other hand, is an instrument we use to view far objects such as heavenly bodies. When we mention heavenly bodies, we're talking about the stars, the moons, and then other planets. So you know how far these objects or bodies are from us on the earth. So a telescope can view the moon, and you can use a telescope and see the moon, and it will give you a high level of magnification. Now when we say magnification, it's because compared to what your natural eyes can see, when you're looking at the moon, it looks very small because it's very far. But when you use the telescope, what you would see is quite bigger than what your naked eyes would see. So that's why we say it gives us a level of magnification, right? So that is a telescope. So we want to look at astronomical telescope. The astronomical telescope is made of two convex lenses. So just like our compound microscope, astronomical telescope is made of two convex lenses. One lens which is closer to the object is known as the objective lens, and then the other lens which is closer to the eyes is known as the eyepiece lens. The objective lens of a telescope, astro telescope, is usually of a larger focal length than the eyepiece lens, unlike in compound microscope. So let's see the working principle for our astronomical telescope. Now say this is our principal axis. We'll have, this is our objective lens, a convex lens. And then this is our eyepiece lens. So you should know that the focal length of the objective lens is larger than the focal length of the eyepiece for an astronomical telescope. Now say this point is the focal length of our focal point of our objective lens, and then this is FO, the focal point of our eyepiece. Now, the astronomical telescope is built in such a way that the focal point of the objective lens coincides with the focal point of the eyepiece lens. Now, when the focal point of the objective and eyepiece lens coincide, that is to say they are at the same point, then we say that the telescope is used under normal adjustment. So the telescope, you should note this down. An astro telescope is used under normal adjustment when the focal length of the objective lens coincides with the focal length of the eyepiece lens. That is to say they are at the same point. So this is going to be my FE. Both of them are located at the same point, right? Now say I have an object. Remember, we're trying to view something that is very far. So say a distance at infinity, we say something that is very far is at infinity. Now, when we are dealing with ray diagrams, an object at infinity is usually indicated using what? Parallel lines or parallel rays. So say we have our object coming as a parallel line from infinity. So say we have this like this, we have this like this also, and then we have this. We have these are parallel rays of the object coming from infinity. So this would go straight. This would go straight since it is going through the optical center, right? Now, while this would bend, meet at this point, this would also bend, meet at this point, right? So these points, all of them would converge at the focal point. So this is where the image would be formed as a result of the objective lens. So what would happen is that this image that is formed at the focal point since it is coming from infinity. Parallel rays converge at the focal point. So when it forms an image at the focal point, this image that is formed by the objective lens would now become an object to this particular eyepiece lens. So this is now the object for this one, right? Now, which is coming from the focal point. So that the rays from here, when it travels this way, and it hits the lens, this is the focal point on this side, Fe. When this hits the lens, it will do what? It will go like this. Meanwhile, the eye is trying to view it. Is at this point. This is the eyes, right? Now, when you pass again, like this, it goes parallel, right? So that parallel rays are now seen by the eye. So this is actually the working principle for our astronomical telescope, right? Yes. Now, if you watch this clearly, you would notice that the final image is formed at somewhere at infinity, right? To the eyes. Now, we want to look at the magnification that is produced by our astronomical telescope. What is the extent to which this telescope can magnify the object? Now, simply, since we're trying to view something that is far, it means that as you can see these rays coming, they are incident on this lens at a certain angle, right? So it means that for our astro telescope, we, instead of talking of linear magnification, we're interested in what? Angular magnification, because these rays hit our lenses at a certain angle. You can see it. This is the angle at which this ray would hit our lens. So I'm going to call this angle theta 1. And then this ray also enters the eyes at a certain angle, which is this, which I'm going to call theta 2. But we can understand from simple geometry that if this is theta 2, this is also what? Theta 2. Vertically opposite angles are equal. If this is theta 1, this place is also what? Theta 1. Vertically opposite angles are equal. Now, what is the magnification for our telescope? The magnification for our telescope is actually what we call angular magnification, not linear magnification, because we are dealing with angles, right? Now, the angular magnification is the ratio of angle subtended at the eye, angle subtended at the eyepiece, the ratio of angle subtended at the eyepiece to the angle subtended at the objective lens. So that is angular magnification, the ratio of the angle at the eyepiece to the angle at the objective lens. That is our angular magnification. And then, which is simply given as the angle at the eyepiece is what? Theta 2. The angle at the objective is what? Theta 1. So this is our angular magnification, the ratio of the angle subtended at the eye by the object to the angle subtended by the image to the angle subtended at the eye by the what object. So that is what we have as the angular magnification. Now I want to get another relationship for this, but you should note that this angle, an assumption we're making is that these angles are small. If they are small, it means that the tangent of the angles we'll be considering will be approximately equal to the angle itself. So if that is the case, I want to consider the tangent of theta 1 and then the tangent of theta 2. Now, you know that the distance from this point to this point is FO, right? Yes, the focal length of the objective, so that this height is going to be what? The height of our image, which I'm going to call H. Now, tan theta 1 and theta 1, tan is opposite. Tan is opposite, which is the height H, over adjacent, which is FO. The same way, if you want to get tan theta 2 is going to be this theta 2. So tan theta 2 is going to be opposite, which is the height H, divided by adjacent, which is what? FE. So if I use these two relationships, remember tan theta 1 is approximately equal to theta 1, tan theta 2 is approximately equal to theta 2. So it means that I can substitute. I think I'm going to rub the board. It means that I can substitute into my formula for magnification m, which is theta 2. What is theta 2? Theta 2 is simply h over fe all over theta 1. What is theta 1? Is h over fo. So if I solve this, I would have that my magnification m is going to be h over fe divided by h over fo. So I can say magnification is h over fe times fo divided by h, so that h can fizzle out. And then I would have that the magnification is fo over what? Fe. So this is the formula for my magnification of my astronomical telescope. The focal length of the objective lens divided by the focal length of the eyepiece. The focal length of the eyepiece. The ratio of focal length of objective to the focal length of eyepiece is what we know as the angular magnification of our astronomical telescope. So I believe this concept is clear. One more thing I want to mention. Remember I said that the astronomical telescope is built in a way that the focal length or the focal point of the objective lens and that of the eyepiece lens coincides. It means they meet at the same point. So it means that for our astro telescope, the length of the tube, because your telescope is just like this marker, which is a tube. You have your objective lens inside this tube and you have your eyepiece. So the length of the tube L is actually given as FO plus FE. So this is how you can calculate the length of an astronomical telescope, which is same as length of the tube, or approximately same as length of the tube. So they give you a question, say find the length of the astro telescope. You just add their focal length and you get the length of the tube or the telescope. So I believe this concept is clear to you. We mentioned three formulas. One of them we mentioned m is theta 2 over theta 1, where theta 2 is angle at the eyepiece. This is angle at the objective lens, right? Or you can say this angle subtended by image, this angle subtended by object. So we mentioned these three relationships. So please do well to take note of these formulas. So if you have followed this video up till this point, please do well to subscribe so that you can get more videos from me. Hit the like button, comment, and share with 10 of your friends. Tell them this is prime concept. Thank you.